The life cycle of stars. When we look up at the night sky, the first thing that would catch your eyes would be the stars. You would have noticed all stars are different. Some bright and some are faint. Some are different colors. Well, it is true that some stars emit different amounts of light. As for their difference in color, for a long time it was a mystery. In the 19th century, a new machine which was named the spectrometer was made. It allowed astronomers to find the result when you divide the incoming light from an object into individual colors or wavelengths. Egner Hertzsprung and Henry Norris Russell once looked at the stars and examined all their properties, trying to look for patterns. When they made the chart, they were surprised to see the different stages in a star's life. At first, stars were classified by the strength in their hydrogen lines. The strongest stars would be A stars, then B stars, and so on. This system was created in 1901 by a scientist named Annie Jump-Cannon. A few years later, a physicist named Max Planck solved a problem that was once a complete mystery in physics. The color of a star depends on temperature. Then, another scientist discovered that the spectra of stars depends on the temperature and elements in their atmosphere. She also showed that stars were overwhelmingly composed of hydrogen. Due to this, a new system was made. The new system was arranged by the star's temperature, assigning one a letter. Due to an old system being used, the letters weren't arranged in alphabetical order. The hottest stars would be O-class stars, following on to B, A, F, G, K, and M. Our Sun is a G2 star with a temperature of 5,500 degrees Celsius. A digit was used so that a slightly hotter star than the Sun would be known as a G1 star. Over the past few decades, even cooler stars were found, so astronomers had to classify more letters, which were L, T, and Y. During the Big Bang nucleosynthesis, within the first 17 minutes, hydrogen and helium were formed and are the most common elements in gas clouds. Eventually, each huge gas cloud will form a nebula. Due to the pressure of gravity, it spins, and eventually, the temperature will reach up to 15 million degrees and form a protostar. Now it has enough pressure and heat for nuclear fusion to commence at its core. The energy produced during the fusion process will radiate outwards, which will allow the outer layers to expand. On the other hand, the gravity of the star pushes the outer layers towards the core. As long as these two are balanced, the size of the star remains the same. The star shrinks if the gravity exceeds the radiation and expands if the radiation overtakes the gravity. This will create a yellow or red main sequence star and will shine for the next million to a billion years based on its mass by fusing hydrogen to helium at its core. If the star has less mass, it will last for longer than a star with higher mass because the fusion accelerates depending on how much mass the star has. The stars that have one-third of the mass of the Sun are red in color, hence called red dwarfs, which are classified as M-class stars. These stars have a very small core. All the hydrogen fusion happens only in the core, and the remaining part of the star is convective in nature. This means it freely allows the radiation and dust, which includes hydrogen and helium, to rise from the core to the outer layers, which will get cool there and fall back into the core to be used again as fuel. This process helps the fuel to last longer. Stars the size of the Sun are much larger in size than the low-mass stars. It doesn't convect the dust of hydrogen and helium to the convective zone due to its dense radiative zone in the middle to get cool. The star uses up its fuel more quickly than low-mass stars because the core gets more hotter as density in the core slowly increases, so its lifespan is around 12 billion years. The star's brightness increases gradually as the temperature in the core heats up to the outer layer. Now the Sun's luminosity has increased by 40% since it was born. By the time hydrogen ran out in the core started fusing helium as it gets enough temperature and pressure. Hydrogen fusion starts in the radiative and convective layers as it gets enough temperature to do so. This leads the star to expand to almost twice of its size, and also it changes color. Now the star is a subgiant. Due to helium fusion in the core and the convective nature of the radiative zone, the core contracts and the outer layers expand. As the hydrogen fusion in the outer layers, its luminosity increases by 2,000 times, so its outer layers bloat up to 10 to 150 times its original size. The energy or temperature per square meter reduces drastically, which leads to the star being cool. All cool stars are red in color, hence the star is now a red giant. As the star is as the star is swollen, it is now very less dense, therefore the gravity decreases due to radiation overpowering gravity. As the star is swollen, it is now very less dense, therefore the gravity decreases due to radiation overpowering gravity, which allows the star to shed mass, losing one-third of its mass. The force of radiation is very powerful, so material on the surface gets blown into space. In this stage, because the temperature is high enough, helium fuses into carbon. Hence the core absorbs a lot of its energy and expands even further. A lot of energy takes place in the core because of the fusion process, so not as much energy will reach the outer parts, which will cause the outer layers to contract. So the energy or temperature per square meter increases gradually, which leads to the star getting hot. Its size is 10 times its current size and 20 to 50 times its luminosity, so the color changes from red to orange. After a long period of time, carbon builds up in the core, so it contracts and heats up. This pumps more energy into the outer layers, so they get to expand and cool. The sun turns into a red giant again, but this time with even more luminosity and it's bigger. It blows off half of what is left. Once helium runs out and only carbon is left in the core, it turns into a very bright ball of energy. Now the star is a white dwarf. Now it can't generate any more energy, so for the rest of its life, it gradually cools and fades. This process takes a few tens of billions of years. Now the star is dead. The stars that have more mass than the Sun, you would find a completely different story. A high mass star can only live to about 10 million years or so. It starts off its life as a main sequence star like low mass stars. High mass stars live a shorter life than low mass stars due to the star being more powerful, which allows fusion to happen faster. During the fusion process, a lot of energy is produced, which allows the core to contract and the star to swell up into a red supergiant, massive in size. It takes millions of years for hydrogen to fuse into helium. It will take centuries for carbon to fuse into neon, and it will take 1 year for neon to fuse into oxygen. It will take several months for oxygen to fuse into silicon, and finally, it will take 1 day for silicon to fuse into iron. Iron cannot fuse to anything else because it doesn't have enough energy to begin fusion process. Iron is nuclear ash. Fusing iron will not produce any more energy like the other elements. The fusion stops. At this point, gravity wins against the radiation of the star, so gravity pushes the outer layers towards the core at 25% the speed of light, making it smaller and smaller. All the pressure starts to squeeze the core like squeezing the Earth to the size of a city. Due to the high gravity pressure, even electrons and protons also get squeezed into neutrons. This causes a shock wave throughout the star, which causes a great explosion known as a supernova, which outshines galaxies. Till now, we have only seen the formation of elements from hydrogen to iron. During this process of supernova, the other elements in the periodic table form. All the elements in the periodic table that we see now on Earth were created as part of a supernova. After the explosion, the remains of the star form a neutron star. The star is about 25 kilometers wide and is extremely dense. The surface temperature of a neutron star is 1 million degrees Celsius, nothing compared to our Sun, which only has a surface temperature of 6,000 degrees Celsius. Even though this celestial object is a star, it has many properties that stars and planets have. Neutron stars have an extremely hard crust. The outermost layers are mostly made of the iron left over from the supernova explosion. All the nuclei are squeezed so hard that they even touch one another. This is known as the Notch phase. They get extremely squeezed as we move towards the core. Protons and neutrons form long cylinders, which is known as the spaghetti phase. Further down, there is a lasagna phase where millions of protons nestle together, making what physicists called nuclear pasta. This pasta is unbreakable. In the core, protons and neutrons are squeezed even harder that scientists are not sure what properties they have. These neutron stars spin very fast, several times a second. This is known as a magnetar. The fastest magnetar spins 700 times every second. We know almost 2,000 of these in our galaxy, so neutron stars have a magnetic field quadrillion times stronger than the Earth. An extremely rare event is when two neutron stars collide with each other, resulting in an explosion known as a kilonova explosion. This explosion is so extreme that heavy nuclei begin falling and reassembling again. If the mass of the neutron star is over 1.4 times the Sun's mass and less than 2.8 times the Sun's mass, it will remain as a neutron star. That means the gravitational push towards the core is balanced by the radiation by atoms inside the core. It has a very strong magnetic field around as it spins so fast, around few hundred times a second. It concentrates and forms vortexes. It radiates beams from the magnetic pole. This beam also spins along with the star. An aging neutron star's furious rotation slows over the period of a billion years, as it radiates its energy in the form of electromagnetic waves. But what if there was a star that was even greater than 2.8 times the Sun's mass? If that is so, gravity will keep pushing in violently. Once a star is about 18 centimeters, the escape velocity at the surface is equal to the speed of light. Eventually, the star will collapse on its own gravity and become a black hole. A black hole is a celestial object that sucks all matter and energy into it. Just for a quick summary, for the life cycle of a low-mass star, first, a cloud of dust and gas form together to create a main sequence star. Next, the main sequence star swells up and becomes a red giant. Eventually, hydrogen fusion will come to an end, which will allow the red giant to cool and become a white dwarf. Finally, the white dwarf will lose all its power and will turn into a black dwarf, which is a dead star. For the life cycle of a high-mass star, first a nebula forms the main sequence star. Only this time, it is much more bigger and hotter, which is why the star is blue in color. Next, during its life as a red supergiant, it builds up on all of the elements it can produce until it finally reaches iron, which is the heaviest element a star can produce. This allows fusion to stop, which means gravity will overpower radiation and start to squeeze the core, resulting in a supernova explosion. The explosion releases all the dust and gas along with heavier elements, forming a nebula which allows the cycle to repeat. If the mass of the star is between 1.4 and 2.8 times the Sun's mass, it will become a neutron star. If its mass is greater than 2.8 times the Sun's mass, gravity will destroy the star and it will become a black hole. Thank you for watching.